Okay, so to do this transformation stuff, we need to know a little bit more about some functions than we have right now. So again, the idea is basically going to be if I take a function that am either given or that I already know some things about and make some relatively minor changes, like add a 3 somewhere or multiply something by 2 or whatever, then what does that do to affect how the function works, to affect its graph, to maybe affect domain and range, that kind of thing. Again, to be able to do this, we need something to start with. We need some functions in the first place. So we've looked at a couple of these, but turn to blank page in your notes where you have some space. This is a list of things that we're going to add to as we go this semester. But here are 6 example functions that we'll call parent functions or basic function types. They're just going to work kind of like prototypes. Basically, we want to get to the point where I can sort of think about the symbolic version of the function, like the equation, right? Like y equals x squared, and its graph, which looks something like this, and kind of have those be like interchangeable, right? So when I see one, I think of the other, and vice versa. So what I want us to do for the next 5 minutes or so, grab your calculator or in Desmos on a phone or tablet or whatever, graph these 6 things. The first one, it doesn't matter that it's 3 or 5 or any other like constant value, but graph these. Again, somewhere in your notes, just make a little sketch of the graph because we want to get to the point that we recognize the thing from the picture. And then just to the side, maybe jot down its domain and range. So again, we'll start with that. Just graph those things, get a sense for what those look like. All right, so let's just kind of quickly take a look at each of those and talk about some stuff just so we all have it. If you need to spend some more time making the version in your notes nice later, whenever you do that. So y equals 3. Here it is. What is that? Yeah. Yeah, like what? How would you describe the graph of the thing? Okay, a straight line, but what kind? Constant. It's a constant function, which gives you a horizontal line, right? Okay. So for any x value, because it doesn't depend on x at all, right? For any x value, you get the y value here 3, but 5, 7, whatever. It's just a horizontal line. Okay, so constant function is a horizontal line. What's its domain then? X value is where it's defined. Everything, right? All the real numbers. I'm going to write these as intervals, but the whole real line. What about the range? Y values, right? So what Y values or value does that thing include? Just 3. That's it, right? Okay, well, how do I write down a domain that's just got one thing in it? I don't need to write an interval anymore because it's not stuff between here and here. It's just one thing. If you're going to list things out, that's when we use the curly braces. Most of the stuff that we're going to look at, we're more interested in things that, cover some range of things. So we'll do a whole lot more with interval notation than we ever will with just like listing like that. But that's how you would write it down. Okay, so there's that horizontal line. All right, y equals x. Still a straight line, but now a diagonal, right? Think back to the high school algebra or whatever. Y-intercept is 0, slope is 1. So you get that diagonal straight line like that, linear function. What's its domain? Yep. And the range? Same thing, right? Yeah. Talking about the y values now. So again, there's a little bit of a subtle thing kind of underneath all that, that the domain part is because one end is sort of going off infinitely to the left, the other's going off to the right. The range part, it's same idea but up and down. But that's what's going on here. Okay. X squared and x cubed we looked at a little bit last. Golly, there we go. A little bit last week as examples of even and odd functions. But as a reminder, there's the graph of y equals x squared. It's this U-shaped graph. The name is parabola. We'll hit that later, so don't worry about it. But this kind of U-shaped graph is opening upward and has this sort of base point. It's called the vertex. Again, don't worry about that a ton for right now, but it's sort of sitting on the origin, right? The bottom, the point at the bottom of the thing is sitting on the origin. So what are its domain and range? It's defined everywhere over the entire x-axis, right? Or again, if you want to think about it as sort of crushing it down or thinking about its shadow, it covers the whole x-axis. What about the range? The upper half, right? There's a lowest point on this graph. The lowest point this ever passes through is 0, 0. So again, if I think about shadow or crushing it into the y-axis, the lowest point that we get covered up is 0, and then up from there, right? So how do we write that down? 0 to positive infinity. 0 should be square bracket because it's included, because it actually gets there, right? 0 squared is 0, so that point is actually on the curve. All right, x cubed. Again, that was our sort of first example for an odd function, right? That has origin symmetry. What do you see in terms of the domain and range? In terms of the picture, the graph itself, right? It's this sort of weird little, thingy that does this thing, right? Something like that. What about its domain and range? Well, one end's pointing to the left and the other to the right, and everything in between looks like it gets covered up, right? So it's defined over the whole x-axis. What about the range? One up and one down, right? Okay. Those we're probably a little bit more familiar with, right? You hit linear stuff real hard in previous classes. X squared and x cubed, we looked at a little bit last week. These others, the square root function, the absolute value, those might be new. Here's the square root function. What's maybe different or weirder about this one than the others? It kind of like stops somewhere, right? It cuts out somewhere. It's because it's a square root. Don't worry a ton about that for right now, but if you try to take the square root of a negative number, stuff gets weird, right? That's good enough for now. Stuff gets weird. We'll worry about the details later. That's why this thing lives in quadrant 1. It takes positive x values as input, and what it spits out then are positive y values. And 0 is okay too, because the square root of 0 is 0, right? So generally it's not positive, I should say non-negative, but that's why it lives in quadrant 1 like that. Okay, so it sort of starts at 0, 0, and then goes up and to the right, and it's this kind of gradually sloping curve thing. How should I write down or describe its domain and range? A bracket. 0 to infinity. And the range? Yep. Same thing. Yep. Good. It is pointing up. It's a lot more gradual. It's slower here than it was with the others, right? Like there's a little bit of a weird thing if you do the, draw the arrow at the end of the graph. With like x squared, you're drawing it so that it's pointing like straight up, basically, right? Here, it's still going up. It's just a lot slower. Does that make sense? But we're talking about like forever as the scale. So it's still, heading up toward positive infinity. Okay, good. All right, and then the last one here, the absolute value. Okay, we'll talk a lot more about what and why absolute value does what it does in a couple of weeks. But for now, makes negative things positive is fine. So what it does is take y equals x, that one that we talked about before, and take all the negative stuff and flip it back up, right? So it's like you took y equals x, that line, and cut it here and flip that part up so that all of the y values are not negative, right? It's sitting up in the upper half of the thing. Again, you get kind of a corner point or a vertex there at 0, 0. What are its domain and range? Yep. Yep. Okay. Everybody all right with all that? Okay. So again, this kind of sets the stage a little bit for a pretty common theme. Like often the stuff that we're going to look at is either going to be what we will come to describe as nice, meaning that it always works, it's always defined. That's what we see like here and here. You plug in the AX value that you want, nothing's going to break or go wrong. Or if that's not the case, then usually 0 or the difference between being positive or 0 or negative ends up being kind of where stuff gets weird, right? Okay. Now again, sort of our goal is to get to the point where we can kind of recognize these things from their graph and understand what the graph looks like, because the graph tells us about the behavior when we see them. So that on like a hypothetical test question, if I gave you something like that, and that's all you have, just the graph, right? Here's a function. Here's the graph of a function. Tell me about it. You can tell me, okay, well, based on the shape, right? Based on the behavior of the thing, I know that is a, what kind of function? Absolute value. Okay, it's an absolute value. So I go to the absolute value bucket in my brain, and absolute value looks like this, and it lives right here. And so this one lives up here instead. So this and this must have happened to it, and here's what I can say about it based on that, right? We're gonna work out the details this week, but just so you know, that's kind of why I'm having us do this whole like draw all these graphs thing, so that you can get to the point where you recognize it, okay? I'm also gonna make you like hold your hands up in the air and stuff. Okay, everybody good? So far anyway? Looking for Math 110? No, maybe not, okay, all right. So I handed you notes already, right? Yes, good, okay. So what we're gonna spend a little bit of time on now is scan that QR code and it will pull up a graph that looks like this. What this has in it is the color might be hard to tell here, but that red one, that's y equals x squared, right? So treating that as the sort of starting point or the parent function. Treating that as sort of our starting point. This thing in blue, it's what happens if you change this a value that shows up here and this b value that shows up there. So what I want you to do for the next 5-10 minutes, something like that, go ahead and move desks around if you aren't already into groups and get into groups. And then basically just kind of mess around with A and B and see if you can figure out what they do and why, right? So we're working towards something like a rule or a definition for what those things do and how they affect the function. I heard it was. Yeah. Our group text was blowing up all the last 15 minutes before we're leaving, so is it pass out? Oh, good. It's great. Right, so again, like pull the graph up, try messing around with, I would do one at a time. First, change A, see what that does. Change B, see what it does. Try them together, see if you can come up with, sort of a, again, like a rule or whatever for how these things are changing functions. Right. Okay, so tell me what you see. Okay, so Kennedy says changing A moves things along the x-axis, changing B moves it along the y. What do we think about that as a description of what's happening? Something like that. Okay, so changing A changes x values, changing B changes y values. Look at the way that this thing is defined, right? This is the thing that's making the blue graph there. F of x plus A plus B. So where does A show up? Like where does A go if I give it an A value? Inside the parentheses, right? What do the parentheses do for function notation? Like what are those, separating out? That means it gets done first, right? It happens first. Think about order of operations. Parentheses come before anything else. For function notation specifically, that's going to be the stuff that gets sort of plugged into the function, right? That's the input part. Okay, so what that says is if A is, throw some numbers on here. If A is 2 and B is 5, this is f of x plus 2. Okay, so take the thing that you're plugging into the function, add 2 to it first. Then plug it in, do the function thing, then plus b, well, that's outside the parentheses, right? And for order of operations purposes, we treat the parentheses happen first, then you do whatever the function does. Because look at this one specifically, the function part of it is squared. So this one that we're looking at would be y equals x plus 2 squared plus 5. That's what that would be with that a and b and the function being x squared, right? So order of operations stuff, this happens first, then you square, then plus 5 very last, right? So this b value that we're adding on, well, that moves things up and down because it's changing the y values, the output, kind of directly, right? Because it happens at the end like that. It's like you take the y values and make them all 5 bigger than they were. Well, on a graph, what that's going to translate to is the thing appearing to move up. Right? If you make all the y values 5 bigger than they used to be, they're going to sit 5 higher than they did. Okay, so A moves things left and right, B moves things up and down. Can we be a little more specific about how? Because there's one kind of weird thing here that we haven't talked about yet. Adding 2 makes it move to the left. What if we subtract? To the right. Okay, but when we set things up, we put our number line for our x-axis down, and we set it up so that you read left to right, negative to positive. So doesn't that feel backwards then? Anybody else feels like that's backwards? It feels backwards to me. You add, it moves to the left, but that's the negative direction. You subtract, and it moves to the right, which is the positive direction. Okay, there's that. That doesn't happen here. Here you add, and it moves up. You subtract, and it moves down. Okay, so let's kind of summarize that a little bit. I encourage you to not try to think of this as like a set of rules to memorize, like this thing does that or whatever. Try to break down what's going on because there are too many different cases to try to keep it all straight. And then when you sort of 80% remember it, you end up moving things up, right? So Stuff on the inside affects the x values. That's going to move left and right. Stuff on the outside affects y values. That's going to move up and down. So if we add or subtract inside, what's going to happen is that it shifts left and right. That's the thing that in my graph was labeled as A, right? And B, if we add or subtract, I suppose subtract, like that. Subtract outside, it's going to shift up and down. And again, one of those, the left-right stuff kind of feels backwards what it seems like it should do. One way that you can think about that is that this thing that's happening inside, right? Think about your x-axis number line as being like when things are happening. What this does is sort of move that timeline up, right? Like make everything happen earlier. So, okay, well, that means that this +2, everything's going to happen 2 before it used to. So everything moves to the left. All right, so again, take a couple of minutes if you haven't already. Think about these 6 examples here, and just real quick with your group, decide what you think these 2 things are going to do. Right? How does that take the function and change it?
Yeah.
Okay, so the number part affects how far, right? Somebody tell me about 1 and 2. What's the difference in where that +3 shows up? Here it's inside, here it's outside. Okay, so +3 inside here, that's going to move 3 to the left. This one will be 3 up. Everybody agree? We happy with that? Okay. 3 and 4 kind of go together as well. +2. Here, +2 is outside, right? And here it's inside, even though there aren't actually parentheses written down, right? But they're inside the grouping symbol, which here is the square root. Okay, so this is why I keep using air quotes with inside and outside. The parentheses might be sort of implied rather than actually there, but they mean the same thing. Inside, we mean inside the action of whatever that function does. So it could be inside a square like it is here. It could be inside an absolute value like here, inside a square root. Okay, so the one that's outside is going to move everything up. The one that's inside is going to move everything to the left because it was +2. Okay, and then again, this is inside, this is outside. So absolute value of x minus 5, that's 5 to the right, and the absolute value of x minus 5, right? Long pause because it's happening on the outside, moves everything down. Okay. All right, so again, real quick, try to, using just your notes, or even if you want to put those away, but try to just kind of quickly sketch what these should look like. Right, so now you need to know, okay, how's it moved, but also what did it look like in the first place? Right, so identify what kind of function it is. Try to, come up with what that should look like then, and then, okay, how do I actually draw it? Okay, so they're all kind of paired up, right? The first two, 1 and 2, what kind of function are we talking about? X squared, right? What does x squared look like? Before I do anything to change it, what does it look like, sort of by default? Yeah, all right, everybody do some kind of that graph thing, with your hands, draw it or hold it up or whatever. That's what it looks like. Where is it? Where would I, like before I change anything, how would I describe to somebody where that thing lives? That point at the bottom, which again is called the vertex, but that point at the base of the thing sits on the origin. Okay, so it's sitting at the origin, opening up, right? That means the domain, everything, the range is just the upper half, right? What does number 1, quantity x plus 3 squared, right? So plus 3 on the inside. What does that do to change it? Moves it to the left 3. So where does it live now? Negative 3, 0 is where that point that used to be in the origin, that, why do I care about that one, by the way? Not really that I care about that point particularly. It's just that if you think about the shape of that thing, that's about the only one that's really convenient and distinct, like visually, right? That's the one that I can sort of watch and pay attention to. Okay, and you probably did that, unconsciously when you look at the graphs. But so that point that used to be at the origin, now it's going to be at negative 3, 0. Okay. So sketch that in real quick. Negative 3, 0. It's already a U-shaped graph opening up. Something like that. Did that change its domain or its range? No. It was defined over the whole real line before, right? The x values. I moved it to the left. That doesn't change. You know, infinity plus 3 on one side, I guess, or whatever. That doesn't change anything that way. The range, well, it's still sitting on the x-axis, right? That's still the lowest point on the graph, so it's still 0 to infinity. Okay, what does moving it up 3? Oh, sorry. What happens in number 2? Moves it up 3, right? Okay, so now where does that point that I can keep track of easily end up? 0, 3. Perfect. 0, 3. Something like that. Now what about domain and range? Yeah. Domain hasn't changed, but the range has, right? The range used to be 0 to infinity, the whole upper half of the plane. What is it now? 3 to infinity, because that all moves up with it, right? Again, if you want to think about it as, you know, smashing it down onto the y-axis, well, you did that, but then you slid the whole thing up 3, so now the lowest point on the graph is 3. Okay, cool. You tell me about number 3 then. So it's a square root function, right? So coordinate plane, it looks something like that, right? Sits at the origin, kind of hooks off to the right and up in the quadrant 1. And what happened to it? It goes from 0 to 0 to 2. The point that used to be at 0, 0, where the thing kind of starts out, right? That again is easy to like keep track of. That's at 0, 2 now. Does the domain change or the range or both? The range changes, right? Domain's the same because it's still sitting in the same, its shadow would be the same on the x-axis, right? That's domain. That change, or that's the same. That hasn't changed. That hasn't moved. But we did move the whole thing up, so the range would change along with that. Now the lowest, the minimum value for the y value would be 2. It doesn't go down as low as 0 anymore. Okay, number 4, same kind of function, but now it's going to move to the left. Okay, there we go. Coordinates at that point, -2, 0. Okay, and then the absolute value looks like V-shaped graph, opening up, but straight lines now, right? Instead of, you know, sort of curving like the square. So straight line, V-shaped graph shifted to the right 5. So that corner point that was at the origin, now it's at 5, 0. Okay, and then the last one's same idea, but down 5. Okay. Everybody get a feel for that? Do you have any questions about anything so far? So cover up your notes or whatever. What can you tell me about that? It's a cube, right? The first thing I want to look at is like, what type of function is this? If that's going to tell me about the shape of the thing. That's this. So that's if I look at this and ignore any like +2, ignore the -4, ignore the +2, because those are, again, small things that change where it lives that we've just been figuring out how they work. If I ignore those, what's left is the cube. That's the main like action of what the function does. That's the thing that determines the shape. I didn't mean to do it with my hands, but what does a cubic function look like? Yeah, something like that, right? So it's kind of like you took the square thing and sort of flipped one end down. It's a little bit sharper, harsher, but something like that. Okay, and normally, where does it live? That point in the middle passes right through the origin, right? It's an odd function, right? That was our example of an odd function from last time. So that point at the origin, or that point in the middle, passes through the origin. What do these two things do to it? the right 4 up to, so that point that was at 0, 0 should be at 4, 2 now. So the graph would look something like that, right? I'm not trying to draw it, perfectly or anything, but that's where that point that used to be here is now at 4, 2 because we moved everything to the right 4 and up 2. Okay, cool. Questions about anything? Awesome. Okay, so on the back, there are 4 problems there where we are doing all of the same kind of stuff or using all the same kinds of ideas, just maybe from kind of different perspectives. So 7 says, here's a function given to you basically the same way I just did. Tell me about the parent function. What has happened to it? How has that changed it? What does that do to the graph? Like describe it, right? 8, same kind of idea, describe and then sketch the graph. Okay, so now I need to know what it looks like. Obviously, you have a calculator still. I would encourage you to try to think about it first before you jump to that and use the calculator to check. 9, write down the function whose graph is shown here. And this is why, because now I'm asking you to do it from a graph. If you start from a graph, there's no way to put that in the calculator, right? So you have to know something about where it came from. So think about what kind of thing that is, how it compares to the sort of like default thing and what that would mean. And then the last one, write down the function whose graph has the same shape as y equals absolute x. Okay, so it's this kind of graph, but has shifted these different ways. So we are going to pick up tomorrow with those 4 things. We'll spend 15 minutes or something with you guys in your groups kind of comparing notes and talking about what you did, and then we'll talk about it all together and then move on and add some stuff. So what I want you to do tonight is try those on your own, bring it back with you tomorrow so that we can sort of jump right in and you've already thought about it on your own a little bit. Okay, so reminder again, let me pause this thing.